In electrostatics, the rule is consistent. Like charges repel. If two positive spheres are placed in a vacuum, they will violently push away from one another. This behavior is a cornerstone of the microscopic universe, governing how particles distribute themselves in space. Consider a different configuration: two parallel conducting wires, suspended side by side in that same vacuum. When steady current flows through both wires in the same direction, the expected repulsion fails. Instead, the cables bow inward, snapping toward each other. This creates a contradiction. If these currents consist of identical moving charges, the rule of like repels like dictates they should move apart, not together. The resulting attraction is a physical force that can be measured with precision, and it increases as more current is added to the system. The introduction of continuous motion to these electrical charges changes the physical requirements for their interaction. It might be assumed that the wires attract because one has accumulated a net positive charge while the other has become negative. However, the internal structure of a standard conductor prevents this from being an electrostatic event. Inside the metal, for every moving negative electron, there is a stationary positive proton fixed in the lattice of the material. Because the positive and negative charges are perfectly balanced in number, the wires are electrically neutral. They cannot exert an electrostatic force on one another. To identify the source of the pull, the focus must shift away from the copper itself. The interaction is taking place within the empty space that separates the two conductors. This force only emerges when charges are in motion, indicating the attraction is a mediated interaction rather than a direct electrostatic one. Hans Christian Ørsted's investigation into this relationship began with a demonstration during a lecture in 1820. He observed that a current in a straight wire caused a compass needle placed nearby to deflect from its alignment. Ørsted was the first to demonstrate that electricity and magnetism were not separate phenomena, but were intimately linked. He concluded that moving charges, or currents, produce a magnetic field in the space surrounding the wire. This field acts as an environmental mediator, allowing one wire to influence the other without any physical contact. By generating this field, a wire creates a zone of influence that can exert mechanical force on any other moving charge nearby. The geometry of the magnetic field around a long, straight conductor follows a specific pattern. The field lines form concentric circles, centered on the wire, a pattern that can be visualized by the alignment of iron filings. The direction of these circular lines is determined by the right-hand thumb rule. If the right thumb points in the direction of the current, the fingers curl in the direction of the magnetic field lines. This magnetic field is strongest near the surface of the conductor and weakens as the circles expand outward. These circular fields effectively fill the surrounding space, waiting to interact with any second wire placed within them. We can now analyze how a second conductor, wire B, reacts when it is placed inside the magnetic field of wire A. This reaction is defined by the Lorentz force, the total force on a charge moving through magnetic and electric fields. It states that a force is generated when a charge's velocity crosses through a magnetic field. Consider two parallel wires, A and B, separated by distance d, carrying upward currents. Wire A's magnetic field intersects wire B, pointing downward into the plane. The resulting cross-product force points directly left, toward wire A. This attraction is quantified by equation 4.17. The attraction is the geometric result of a moving charge crossing a perpendicular magnetic field. The system is reciprocal, adhering to Newton's third law. Just as wire A influences wire B simultaneously generates its own field, BB, which exerts an equal and opposite force on wire A. Equation 4.18 confirms this symmetry, stating that the force from B on A is equal and opposite to the force from A on B. Reversing the direction of the current in one of the wires changes the outcome entirely. Flipping the current reverses the velocity vector of the charges, while the magnetic field vector from the other wire remains unchanged. This reversal causes the cross product to flip as well. The force vectors now snap to point outward, physically pushing the conductors apart. This establishes the rule of the interaction. Parallel currents attract, while anti-parallel currents repel. This predictable interaction shifted the study of magnetism toward metrology, the science of measurement. Historically, it was difficult to establish a standard unit for the invisible flow of electrical charge. While counting individual electrons was not possible, measuring the physical force exerted between two wires could be done with high accuracy. The mechanical pull between these wires serves as a proxy for the amount of electricity flowing through them. This interaction bridges the gap between the invisible motion of charges and the tangible world of newtons and meters. Equation 4.19 is used to define the force per unit length between two idealized conductors. The standard requires two infinitely long parallel wires locked at exactly 1 meter apart in a vacuum. The 1946 definition states that 1 ampere is the constant current that produces a force of 2 × 10 to the -7th newtons per meter of length. This value anchors the coulomb, the unit for the quantity of charge that flows through a cross-section in 1 second when the current is 1 ampere. The strength of the magnetic field itself is measured in Tesla, named for Nikola Tesla. 1 Tesla is the field strength where a unit charge moving at 1 meter per second, perpendicular to the field, feels 1 newton of force. Modern electronic standards remain tethered to this specific mechanical pull between two parallel wires.